In this video, we are going to look at the first real application of derivatives that we've seen. And we're going to see variations of this application again and again throughout the rest of this course. So this is called marginal analysis in business and economics. So marginal analysis is the analysis of the rate of change in business and economics. So if C of X is the total cost of producing X items, then C prime, the derivative of X, is the marginal cost. It represents the instantaneous rate of change of the total cost with respect to the number of items produced. If R of X is the total revenue, then R prime of X is the marginal revenue, and it represents the instantaneous rate of change of total revenue with respect to the number of items produced. Profit, R of X and if R of X is the revenue function and C of X is the cost function, then P of X is R of X minus C of X, which means that P prime of X is equal to R prime of X minus C prime of X. So the derivative of profit is the derivative of revenue minus the derivative of cost, and this is the marginal profit. The marginal profit is the instantaneous rate of change of profit with respect to the number of items produced or sold. Now, we have an example. So a company manufactures and sells X radios per week. If the weekly cost and revenue equations are C of X, the cost is $5,000 plus 2X, so $5,000 fixed plus $2 per unit. And R of X is 10X minus X squared over 1,000, and we allow X, we can manufacture and sell somewhere between 0 and 8,000 radios. We want to know the approximate changes in cost, in revenue, and in profit if production is increased from 2,000 to 2,010 units per week. Okay, remember we're being asked for approximate, so we want differentials. Remember, the marginal cost, revenue, profit are the derivatives of cost, revenue, and profit. So I've rewritten the important parts of this problem on the next page so we can work this out. So we first want to calculate the marginal cost, revenue, and profit. So marginal cost, C prime of X, is equal to 2. This kind of makes sense, right? This effectively says every additional unit we produce costs us $2 more, $5,000 fixed, $2,000 per unit. That makes sense. R prime of X is equal to, take our derivatives, 10X, the derivative of that is 10, minus X over 500, right? So we bring the 2 down, 2 over 1,000 is 500. So we know P of X is equal to R of X minus C of X, which means that P prime of X is R prime of X minus C prime of X, which is 10 minus X over 500 minus 2, or 8 minus X over 500. Now we want to know the marginal cost, revenue, the approximate cost, revenue, and profit when we change X, when we increase production from 2000 to 2010. And so if we think about this, this is for asking for approximate, so we want DC, the differential, is equal to C prime of X times dx. dr is R prime of X times dx, and dp is P prime of X times dx, or R prime of X dx minus C prime of X dx, which is dr minus dc. Okay. So first we need to calculate C prime, R prime, and P prime. Well, I might not calculate P prime because I can just take the difference here. So C prime and R prime for X equals 2,000. So C prime of 2,000 is equal to 2. R prime of 2,000 is equal to 10 minus 2,000 divided by 500. This is 4, so this is 6. So DC, the approximate change in cost when we increase production from 2000 to 2010, is 2 times dx, which is 10, which is 20. So we expect that we increase production from 2000 to 2010, costs will go up by approximately 20, and actually they do go up by 20. dr is equal to r prime of x, 6 times 10 equals 60. So we would expect that as production goes from 2000 to 2010, revenue goes up by $60. dp is 60 minus 20, which is just 40. So we expect profits to increase by 40. So again, we're trying to find an approximate. The problem says approximate. Find the approximate changes in cost, revenue, and profit if production has increased from 2000 to 2010. We took the derivatives, which is the marginal cost, marginal revenue, marginal profit. We calculate the differentials, dc, dr, dp, and we find dc is 20, costs go up by approximately $20. dr is 60, revenues go up by approximately $60, which is good, so profits go up by approximately $40. All right, let's look at another example. Revenue from demand. So a company manufactures and sells X widgets per week. Weekly demand is given by X equals 1500 minus 100P, where P is between 0 and 15. P is price, X is demand. We want to find the approximate change in revenue if production is increased from 1,000 to 1,050. Again, I've written the important information on the next page so we can do the work. We want to find the approximate change in revenue as X goes from 1,000 to 1,050. Okay, well, first off, we know revenue is X times P. X is changing, so we need to get rid of P in this equation, and we don't have the right form of our demand equation to do that, so let's rewrite. So X equals 1,500 minus 100P. 100P equals 1,500 minus X. P equals 15 minus X over 100. Okay, so now we can rewrite our revenue equation. Revenue equals X times P, 15 minus X over 100, equals 15X minus X squared over 100. Okay, so there's our revenue equation. We're trying to find an approximation. X is going from 1,000 to 1,050, which means dx equals 50. We want an approximation, so that's going to be dr equals r prime of x times dx. We need to calculate r prime of x, multiply it by 50. So r prime of x equals 15 minus x over 50. Right, because we brought the 2 down, 2 over 100 is 1 over 50. Okay, we need r prime of 1,000 is 15 minus 1,000 over 50, which is 1,000 over 50 is 20. So 15 minus 20 is negative 5. Okay, so go back over here. We're using our differentials. dr equals negative 5 times 50, which is what dx is, which is negative 250. So revenues go down by approximately $250 when production goes from 1,000 to 1,050. So from a revenue perspective, this is not a great strategy. Okay, average cost, revenue, and profit. So same kind of idea, but we're talking about average cost, revenue, and profits, and we have to be a little bit careful. So we can carry out marginal analysis relative to average cost, revenue, and profit. The average cost, and we typically denote this with a bar over the letter, so C bar of x, average cost, is C of x divided by x, R bar of x is R of x divided by x, and P bar of x is P of x divided by x. The marginal average costs are given by C prime bar, C bar prime of x, R bar prime of x, and P bar prime of x. So we take the derivatives of these functions. Now, it's really important. You've got to divide the function by x first and then take the derivative, as opposed to taking the derivative and dividing by x. You will get two different answers. Okay, so a company manufactures tennis rackets with a cost given by C equals 400 plus 5x plus 1/2 x squared for x bigger than or equal to 1, where x is the number of rackets produced in an hour. We want to find the average cost and the derivative of the average cost, and we want to find the approximate change in average cost per racket if production is increased from 20 to 25. Again, we're doing an approximation here, so we're using differentials. So here are my equations, and here's what I want to calculate. dc equals, dc bar is c bar prime of x times dx, right? Differential is the derivative of the function dx. Okay, so we need to calculate the average cost function. We need to take its derivative. We're going to plug 20 into the average cost function. Dx is 5, and we're going to calculate. Okay, so C bar, the average cost, is simply the cost divided by x. So 400 divided by x plus 5 plus 1/2 x. And I'm just going to rewrite this as 400 x to the minus 1 plus 5 plus 1/2 x. This is my function. I divided cost by x to get the average cost. The derivative of the average cost is easier like this because everything's in the numerator. Negative 400 x to the minus 2. Derivative of 5 is 0 plus 1/2, which is negative 400 divided by x squared plus 1/2. Okay, so these are my costs, my average cost, the derivative of average cost. We need to plug in 20. Derivative of average cost at 20 is equal to negative 400 divided by 20 squared plus 1/2, which is negative 1 plus 1/2 is negative 1/2. So the approximate change in average cost is negative 1/2 times 5, which is negative 2.5. So the average costs are going down. And that kind of makes sense, right? You've got some fixed costs. We can see it here. You've got some fixed costs, $400. And then you've got a little bit of a strange form, but you've got some costs per item, and the cost per item has this extra 1/2 x squared term in it. But you've got some costs per item. As you produce more items, these fixed costs get spread out over more items, and so you would expect your average cost to go down. So we ended up with an approximation. dc bar is equal to negative 1/2 times 5, which is negative 2.5. So the average cost is going down when x goes from 20 to 25 by approximately $2.50 per unit per tennis racket.